Do you have my midterm?
I have it in my office, so I'll give it to you when you're quizzing.
Okay. I can also pick it up on mine too, if that'd be easier.
Yeah, no, it'll be fine. I'll just get it with the quiz.
And then for the lab too, there was a video online for Blackboard. Is it fine if I watch that video, or do I have to?
No, yeah, it has to be in person.
Okay.
I'm doing lab makeups this Friday.
This
if
Friday?
you're around.
Okay. Is that normal lab times?
I actually don't know what time we had decided because it was just one student, but I was thinking of might be around here at 11 a.m. or so.
Okay.
I don't know if that time works for you.
It should. Yeah. No, I think tomorrow.
Yeah.
Okay. Tomorrow at 11. Yeah, that should work.
Okay, that sounds good.
So yeah, I can do that then.
Okay, yeah.
And then I don't think there's anything else. I have the chapter 16 homework or whatever. I just forgot to turn that in before the midterm. I got it done.
Yeah.
And it's just chapter 17 and all that stuff. I have that done pretty much. I don't think I'm missing anything else.
Yeah, that sounds good.
Okay.
I would have to look at your.
Yeah, I'm just trying to figure out. I'm lost trying to get back with everything after being sick for so long. I just want to make sure that I'm somewhat on track besides the labs.
Yeah, we can always take a look at everything on tomorrow too.
Okay.
In case. I don't think you missed a quiz because we didn't have a quiz last week.
That's what I was listening to.
Yeah. Yeah, so there wasn't a quiz.
Okay.
We just did midterm corrections.
Okay.
So yeah, you should be caught up then.
Yeah. Okay. So in the lab tomorrow.
Yep. This one. I think they're in my office.
Okay.
Yeah, I can bring more
Okay.
later.
Then do you want?
Huh? I mean, you can take that one now.
Okay. Well, I just need to.
Okay.
Oh, well, maybe I can just wait until.
Oh, okay. Yeah.
Yeah.
I just didn't drag all the papers with me right
Okay.
now.
Can I take that?
Yeah.
So, you
No.
Okay, I can just print it out.
No, I have it all in my office. I
Okay.
just forgot everything.
Yeah, no worries.
I'll go grab them, I guess.
I copied it, so maybe it'll let me paste it. But there's no difference.
Yeah.
That's so weird. Oh. You didn't stuff yet? Yeah. How far in week 7? Week 7 is just it's mostly the bottom line, like the comments, tutorials.
Yeah. Oh, I finished that.
You did? I have to do this. Let's do this.
Well, other places.
Try it. Just try just this liquid. So R equals. What's gonna happen? Shouldn't need to have an equation for it. But,
Yeah.
oh, I need to.
Yeah. Yeah, they're gonna, they do this thing about I want you to see something.
Well, you also need.
They'll last for 50 years.
Do you?
I think his notes say the same, but like a lot of people are sad to get those jobs covered.
But I think there's no like clock or anything.
Oh, she wrote this one.
Try with it.
I'm like, I'm the only one.
That's actually it. That's like the most. Yeah, see, now she's running around. That's so crazy. It's so happened out. It's so whatever. All right. Thanks. Yeah.
All right, happy Thursday. Any questions or announcements or anything? We do have, don't forget, come on. So we do have the guest speaker tomorrow. And so that's tomorrow at 4 p.m. at HEC 132, so the big lecture area. So if you go in person, I think there'll be a sign-in sheet. And then, like I said, there should be a video YouTube link later. And either way, you can earn 5 points back for that. And then we'll have our quiz today, our last chapter. So we're kind of on track. So week 8, maybe we should just look at the calendar real quick. We're getting to the end of the quarter.
So we have to go to the beach to get photos.
Yeah, if you want to do that. And, huh? Yeah, downstairs, 132. And so just looking at where we're at, so just 2 more chapters coming up. So next week we start chemical equilibrium, and hopefully you like equilibrium because this will be the theme continuing on to 3rd quarter. So a lot of equilibrium algebra reactions. And then week 10 we'll finish with acids and bases. And then obviously exam week 11 we'll review on Tuesday there. And then rough draft paper, I would like it due by week 10. That would help me with the grading immensely. So that's kind of where we're at here.
What week are we on now?
Week 8. So we're just finishing up week 8 here. And then, yeah, so only 2 more weeks left. It's coming fast. All right, any other questions? Oh, we should also talk about, so next week, right, you'll have your last lab, and then week 10, you'll have some sort of lab exam, just like last time, and checkout process. So doing some mini experiment or something on your own, and then checkout. So just, and then that will take place right during your regular lab time. All right, so I did want to do that derivation that I had mentioned last time, except I couldn't find where it came from. So part of the problem, not the problem, but just right, we have a lot of labs, and apparently this is from our last lab. We've kind of changed the order over time, as they're all not perfect for different reasons. We've kind of gone over them. But there's no perfect order. You need a lot of information to kind of complete the lab. So I printed out the bonus page from your lab. So this is next week's equilibrium lab that goes over this, or asks about it. So that's where the assignment was from. I couldn't remember or find. And so I did want to go over it because, again, it's good to kind of understand this. And so kind of recap of where we were. And again, we can think back to the urea lab as well. This one is specifically talking about sucrose. But either way, so if we're looking at this one, or again thinking back to the urea lab, so we had our urease, then our urea. And so we had that same sort of scenario again in our lab where this first step is fast, and then then you did that second step, and the urea breaking down of course gave the color change, and so that's what you were observing, right, this slow or rate determining step there. And so now we just kind of want to go through this derivation here and kind of show the rate laws and kind of relate them and what this is showing us. And so we could start off with kind of our basics. And so the first thing you want to do, and if you were, I was trying to find a paper to also help put this in context, but I'm having 2FA issues currently. But basically all the papers kind of start off this way if you're looking at an enzyme substrate. So again, we're looking at, oh, I can rewrite this. We'll call this, right, reaction 1 here. So again, that's just our enzyme plus our substrate binding. And what that is, so we'll call this K1 in the forward direction, obviously K-1 in the reverse. And again, that binding, which I'll just remind us that it's fast. And so we can just write our rate. Sorry, let me close And so we can start off with just writing, our rate of our forward reaction. And so, of course, that would be dependent upon K1 times, our enzyme substrate times our concentration of substrate. And then we want to look at, well, how do we break down this ES, right? So we have, once it's bound, and of course, we could look at this glucose, or sucrose, example here, right? So here's sucrase enzyme providing our active site, showing it binding. And so now we want to analyze, well, how can ES break down? So obviously, we could do this backwards reaction. So now let's go. So break down of our enzyme substrate. And so, of course, again, it's either the breaking down in the reverse direction, from our binding, or what's the other way that our enzyme substrate breaks down? We can look at this reaction. Yeah, the enzyme, So, of course, going forward with this slow reaction. And so let's go ahead and just write that, again, generically. So we're saying, and this is our step 2, so this could be, K2. So, okay, so then, just like you said, so plus K2 times our enzyme substrate concentration now. So here's our breakdown, and then we can just kind of mathematically rearrange this for our derivation. So just pulling out our K's. So K -1, because they're both ES's, so plus K2 times ES. And so now we are saying that if we want to quantify this, so now our forward and breakdown reaction rates have to equal, because again, they're in equilibrium, and this is our fast step. So show ES breakdown. And so again, now we're saying, so we said our formation of ES has to be equal then to our breakdown of ES. Again, fast step. So now we're here. And then let's solve in terms of our enzyme substrate. So solve for enzyme substrate, because we want that concentration. And so why we want that? Because we want to plug it into this one, eventually figure out our slow step. We're just trying to quantify, again, all the ways that ES is being formed here, our enzyme substrate. And so just rearranging our equations, so now we have K1 times E times our substrate over our rate. So K -1 plus K2 here. And so now we can just kind of simplify. And so again, looking at our sheet here, kind of the problem, question 1 there is trying to get us to write it in our steady state approximation. And so now we can call all this Km, is what we're saying, So this is our overall K for the reaction that, again, you quantify this with your urea one. But okay, now we're kind of breaking down where that Km came from. And so again, I'll just rewrite this now. So Km is equal to, then the inverse of this, so k negative 1 plus k2 over k1. So now we can get our equation. So this is kind of looking more like your lab maybe. So now our enzyme substrate is equal to, right, your enzyme times your substrate concentration over Km. So now here's our steady state approximation. And so again, right, this is relating our Km from lab, so yay, you'll be able to get that rate constant.
KM is the inverse of KN?
Sorry, what'd you say?
So KM compared to the regular KN is the inverse?
Just the way we set it here. So I just wanted to set our variable, right, so that we could set it over Km. So this is similar, right, to what we plotted, because we're plotting and getting our y-intercept right back from lab. So this is just defining what K is, right? So because the K's don't really matter, we kind of emphasize that, right? Because you can just obviously, right, punch in new numbers. Now you just have a new effective K. But this is just formally saying, okay, it's equal to this. So Km is equal to, right, this inverse. And so now we can just write it E times S over Km. So that's the same equivalent statement there. And so again, right, all we're saying is now this is our steady state approximation. Since again, those rates have to be equal to each other with our forward and breakdown reaction. And so now we can continue here. And so now kind of step 2 of this little handout sheet that gives you a hint of what it wants you to do next. So once we're at this steady state approximation, then it says to use this relationship. So now we have, right, our enzyme at some point in time is equal to our enzyme total that we started off with, right, minus, and this makes sense, whatever is bound in our enzyme substrate. And so now it's saying that we could plug this in for E here into this steady state approximation, so we could solve for this. Now we'll just say, so using above relationship, plug into steady state. So I'll just rewrite the steady state again. So again, we had that our enzyme substrate concentration was ultimately equal to our enzyme times our substrate over our new rate that we're finding right in this reaction, Km here. And so now we can plug in for E. And so now is equal to, so to figure out how much enzyme is left, right, again, we start with our enzyme total minus whatever is bound to our enzyme substrate. And now, of course, all this times our substrate. So over Km equals enzyme substrate. And so now it's algebra time. So it wants us to solve for ES. So that's what the, again, on this handout says, right? So solve for ES. And so that means, right, we have to do a little bit of algebra and rearranging here now because we have 2 ES's. And so now let's just do that. So distribute So enzyme total times our substrate minus enzyme substrate times substrate all over Km still. And so now moving Km, actually we're going to have to so I'm just algebraing right now. And to put all the ES's on the same side. So plus, oops. So again, there's algebra, so now we can re-pull out our enzyme substrate. So now times Km plus substrate is equal to our total enzyme times substrate. And divide again. So now enzyme substrate is equal to our total enzyme times substrate.
What do you times substrate?
Which part?
It was ES times substrate. Why? We were like, oh, it's
Because it started here. Well, because right, this is where we substituted it in from, right? So it started here where it was multiplied by this substrate. And then, yeah, we use this new relationship, right? Because we basically just wanted another way to express the enzyme substrate value, right? So that's why they said, okay, use this now, plug that in for E, try again, right? Blah, blah, blah. So where we are on the algebra. So now we're left with Km plus S over here. And so now, sorry, I always forget the last little bit of this derivation. Plug in ES. Sorry, I don't understand the last little bit of my own notes, which is always a problem. Because then I put in plug in ES. Now I don't even understand what I meant by that. Oh. Let's see, I'm trying to find other expressions for ES. So in my notes, let's see, maybe y'all can help me to interpret this. So plug in, this is what I have for ES, which is what I've confused up my own notes. So then we have, so if we're trying to solve for ES, then our rate, right, is equal to K2. I think that's what it's just going for, that our rate is actually K2 here, because that's all that's changed from here to here. So I think that's all we're saying, is that we're using our K2 rate now. So once we're at this point. And then kind of the next approximation here with our substrate. And so kind of the next assumption is that our substrate concentration is much, much greater than Km, so that essentially this term goes away. And so then we're left with our rate is our K2. So Km, right, was just all the rate laws, so this, but it's also what we're solving, so we're going to get it out again. So then we have K2 times our initial enzyme times substrate now, and then we simplified it, right, so over substrate. Well, that cancels now. And so now we're just saying that rate is K2 times enzyme time, which is R max here. And so now if we replace ET with R max, so now we're just saying that our rate then is our R max times our substrate over substrate plus Km there. So just replugging it back into here. And so again, all that is just to kind of remind us where we were going with our lab 2 and kind of how it works out. So again, right, then we're left. So this is from lab, right, our line equation. And this is, again, just right from your lab, what we were plotting. So you're plotting your seconds for your first kinetic lab, right, which is inverse of your rate. And then, right, you get Km over R max times 1 over S. So again, right, this was X plus 1 over R max there. And again, right, so then I think most people are ending up with a plot something like this. So 1 over S, and again, T on this time, which is inverse rate. And so that is, again, why we can do this graph for our steady state approximation, and we get our rate there. And so, again, if you were to look into like papers and stuff, I apologize that I couldn't get into my credentials, but you'll see a lot of the math that starts off like that, right? So it's just like putting things in terms of the forward reaction, backward reaction, setting things equal, and, you know, manipulating from there. All right, let's do more practice problems. So let's go back to the homework now. And I did bring copies of the homework in lab. So let's see. Let's look at 5. So kind of practicing with these rate laws. So again, we have our mechanism. And so figure out how to write our balanced equation, right? What does that mean? You got to cancel out all those intermediates. So add up everything on the left side, everything on the right side, cancel out what's the same. And then see if you can write the rate law again just based upon the mechanism. So I'll give you a few minutes to start with that. So let's at least hear your balanced reaction. And this one might be a little tricky. So what did you kind of notice too when you're trying to figure out your balanced reaction? Yeah, Vaughn?
There is more of, you have to multiply B and C to create, to have all of the A stuff or something.
So multiply, you said B, and so these last two, so like these whole, yeah, so that's the weird thing about this, is they didn't really give you balanced equations to even add. So yeah, you had these two A's, and had to recognize, yeah, so times 2, and then that meant the second one also, or the third one times 2 to balance that out. So tricky first step there. And then, right, get rid of any intermediates, so that goes away. We do have 2b though, and then ab should go away. And so then adding everything on the left side, so then that leaves us with a2 plus 2b plus 2cd gives you 2ac plus 2bd. And then do we need another minute or so for the rate law here? So I'll give people another minute or two for that one. And so I know it says to express it in reactants only, right? But if you're struggling, just what is that rate law for that one slow step? Just start with that. Yeah. So right, if we change this one to match the top, well then we have to distribute across, and then we would get 2AB, but then we have just 1AB there, so that's why we decided it was necessary to also multiply this whole reaction by 2. So before we jump to the answer, so what's the rate of our slow step? Let me pick up something else. Kaden, what are we thinking? So what's our slow step? Yeah, the middle one, right? So then it's going to be dependent upon the reactants, right? And so we can just call this K2 since it's the second one. And so literally it's just rate equals, right, K2 times A times B. And again, right, this is just a slow. But then what's the problem with this? And why we need to do some rearrangement? What is it asking us to? Anyone can jump in. So not that there's 2 of them, but what does it ask us for? So yeah, in terms of reactants though, right? So this is a correct rate law expression. It's just not in terms of the reactants. So then your next question is, right, so A is not a reactant, right? So we're looking at our balanced equation. Well, we don't have A in there. That's an intermediate. And, you know, maybe you want to write that. Okay, so it's intermediate, so we can't use that in our final answer. But we can find, right, the rate of A then. So then what's our rate law for our first equation? And you can give me some equations to just kind of help us, or
Rate law would be the a squared to the rate of
Yeah, so basically, so A squared, right, and then in the reverse direction is equal to, yeah, K1 times A2, just like you said. So that's the first step you have to recognize, or right, our first relationship. And again, all we're doing is we're just writing our fast approximation. So yes, they have to be equal to each other. They're in equilibrium. So as fast as one is being consumed, right, the other is made. And so then all we can do is rearrange for A, right? So we need to solve for A because we need it in terms of A2. And so now doing a little bit of algebra, so dividing by K1, so we get our A is equal to K1 times our A2 over K negative 1, so just our new constant, and then take the square root of that, right, to give us A. So essentially, our rate then is equal to, of course, A2, the 1/2, right, since square root 1/2. And so now we can plug this in for A. So now our rate, right, is K2 times A2 to the 1/2. And then, right, B is fine because that is a reactant. And so we're just showing that it's first order with B and then half order with A. Because we had to take the square root, right? Because you had, so it started from here, right? Because your A2, so forward direction, this is the forward reaction, right? Is K1 times A2, your dimer. Oops. And then that has to be equal to the reverse direction, which is A times A, right? Which is why I just put A squared. And then we just algebraic. So divided by K1, and then the square root, right, to get A. So then this is our new rate. So new K, whatever, doesn't matter. Does that make sense? Yeah, and so we could change K2 to just generic K, but yeah, just some sort of K, whatever. We didn't solve for K, but yes, just as long as it's half order with your A2 and first order with B as they are reactants. So does that make sense to everybody? Kind of what we did? So let's just try 6. I feel like we need to do more practice with this. Let's just see how 6 goes. So practicing our 2-point equation.
For the slow step, we found the rate to be K2 times A plus B. But in the slow step, it's 2A plus B equals A. For number 5.
Yeah.
So that 2 at the beginning of the step, it's a little arbitrary because you're not really that concerned about it, or like what happens with that 2? So the first thing you wrote, the rate equals K2 times A times B.
Yeah.
Is that 2 on the slow step, 2A plus B? Is that factored into that at all?
We didn't really factor it in, but just because it's more to balance it with the rest, right? So we were just kind of focusing on that first step. So yeah, it was appropriate to just kind of write it as A plus B, because that's the mechanism itself anyways, yeah. Because, well, it's also kind of different too, because, right, we were trying to do the coefficients to balance it, but then the mechanism itself is just suggesting, right, that it's bimolecular, as in 1A reacts with 1B. So that's why we can plug it into there, right? Because it's about the mechanism step of,
We can simplify it.
yeah, yeah.
And so that's why you don't write into the second order.
Right, because then that's starting to imply too that like now you need 4 things colliding, but that's not what we're saying. It's like the mechanism is just 2 things, yeah. Even though equivalence wise you need 2 equivalents of those reactants, right, to balance with your steps, but mechanistically we're just evaluating it. So 6, there's like 2 different forms of the Arrhenius equation, but they should both work either way. We'll test it out. I think the answer key technically has a slightly different form of this, but it shouldn't matter. Let me try to plug it in with this one. And so again, right, you just want to keep your Ks consistent with the temperature. It really doesn't matter who's K1, who's K2, just as long as you don't swap them around. So let's see, I'll do K2 at the higher one. So it says calculate the rate constant. We're given activation energy. So natural logs, we're trying to find K2. We have K1 is equal to, nothing too tricky here, right? Just joules per mole. So, okay, we're in our standard units, which is good. Over R, so 8.314 for, again, right, joules, moles, Kelvin. And then times 1 over T1 minus 1 over T2. And so now just math. And again, right, answer key showed another form of the equation. They should all work out. And we were in Kelvin, so everything, again, I'm just double checking that there was nothing tricky on the units on this problem. And so now we're just mathing. And so now we have, so now I have my natural log of K2 over 5.5 times 10 to the negative 2 is equal to 0.065. And then we can get rid of natural log by taking it to the E. So E, so K2 over 5.5. And then E to this. So 1.067. And so now we can solve for K2. Oops. Which gives us about, so agrees with the answer key, right? 5.9 times 10 to the negative 2. Inverse seconds there, or 0.05. Well, we have 2 sig figs, so I guess we'll round to 0.059. So times 10 to the negative 2 inverse seconds. So again, just kind of emphasizing that these two forms of the Arrhenius equation, I'll show the answer key from, so this is just, the answer key online, come on. And right, again, different form of the Arrhenius equation, same thing. So right, I think you'll find that in your lab today too, right? I think your lab, I forget which form it shows you. It really doesn't matter. They should give you the same. Okay, yeah. And this one, again, is just fine. I don't like it personally. I like this one just because it's a little cleaner, in my opinion. But, you know, use whichever one feels good. See, we're kind of running out of time. Let's maybe look at this one, but maybe we want to revisit this next week, just because of time's sake. So I think this would be a good one to pick back up. Like I said, maybe next week, go over the answer, because this is a good one that I think shows kind of what's going on. Unless y'all want to do it now. Do you want to just do it now? Okay, let's just go for it. So this is kind of putting everything together, in my opinion. So a little bit of chapter 17, right, and then chapter 18 is down here. And so I shamelessly stole this from the OpenStax textbook, by the way, which, anyways. Your textbook is much more detailed. I love your textbook. I won't go on a rant. All right, so what we should start off with doing is, again, right, so kind of now you're thinking chapter 17 over here, right, examining rate laws. So just trying to figure out the orders based off of our experiments here, right? So obviously it gives us the reactants. And so kind of do that step. So, right, that's the first step here. And again, right, that's relating back to chapter 17. So we're just trying to figure out the overall rate law. And then what we want to get into with E here, so we can kind of skip some of these other problems. But what I care about then is, right, figuring out kind of the rate determining step from this, because I think that will help us kind of see. So let's just start off with that. So again, first step, just examine this data, and let's see if we can determine the orders of NO and H2. So write 0, first, second, kind of where we're thinking, and then we'll go from there. So just the orders. So what are we kind of noticing? And we can start with, let's look at NO maybe. So what do we find for NO with the order? Yeah, so remember, right, coefficients don't necessarily matter, right, when we're just trying to figure out the order. So your observation is good, right? So we just want to focus on that. So this is probably the data set that we want to look at, right? So notice H2 is unchanged. And then you said, okay, well, this went up by 2. Well, then the rate went up by 4. And so then, right, that's implying second order for our NO, right? And then, so what do we find for H2?
Just a clarifying point, it's the second order, since you're taking 4 and dividing it by 2, is that 2, right?
Yeah, the fact that this went up by 4 and this went up by 2, yeah.
Okay.
So then, yeah, Crystal? Yeah, so you're trying to just compare, so you mean you were looking at like these two for H2 then? Yeah, because what you have to have is like one of them has to be held constant, right? And so that's why probably for H2 you want to examine the first two. So NO's constant, so that's not having an effect. But then, yeah, we're doubling H2 it looks like. And then so what happens to our rate from 1 and 2 if H2 is doubled? So it looks like it also doubles. So then, right, since they both went up by the same factor, then H2 is going to be first order. And so again, right, this is just chapter 17, rate law, right? And again, we have to determine rate law from data. And so that's what I'm trying to emphasize by like walking through this problem, right? Is like, we need the data. So again, right, start that like, need data to determine rate law. So it doesn't matter any of these coefficients, blah, 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 right? We need the data. Okay, now that we have the data, and again, we should put some sort of K, doesn't matter. Okay, that's our rate. We have our data. Now, the whole point of chapter 18 is like, okay, now that we know that this is the observed rate law, what's the mechanism that matches that observed rate law? Right, so now this is chapter 18. So now we're saying what mechanism would match, right? And then we're thinking rate determining step. And so essentially, right, we're trying to say how do we combine these steps, right? Maybe the first one is fast. And I'm just, again, just kind of saying that because, well, we need NO plus NO, right? And so now that's where we're trying to get it with the rate laws. We're trying to understand what is the implication of, right, this rate law. What does that mean for the mechanism? Because perhaps this is saying, right, that two NOs have to come together. And so that's why I'm thinking like, okay, this first step, you know, maybe it's fast. Get our two NO squared. And then go on to react with H2. So I'm just kind of surmising. So kind of look at that for a second. Examine that, right? See if you can determine which is a rate determining step. I'll rewrite our rate law, right? Because again, that's the point of the mechanism. So the mechanism is telling you what has to come together, right, in these either unimolecular, bimolecular reactions, but then that has to match with your rate law. That's all we're saying. And so if our mechanism is consistent with our rate law, then that's a good sign that we're understanding mechanistically what's happening.
H2O plus N2O can equalize into N2O2 plus H2. Is that the point?
Yeah, but then the question is, right, so you're still trying to figure out what's kind of the rate determining step, right? So that's kind of, and, you know, let's look at step H2. So, right, so kind of what I'm looking at is, well, I don't want to get too crazy with these rate laws. And I'm kind of thinking, you know, maybe this is fast, this last step, in which case, right, we don't really care to quantify that. But let's just kind of assume this is slow. And so kind of right back to what you're saying. Okay, so our implication is that our K2, right, is equal to H2 times N2O2. And again, right, if we're assuming it's slow, then it must match, right? So that's what we're saying, right? Whatever step that is a slow step, it's going to match the rate law. But we're going to have to express it, right, in terms of the reactant. So that's the whole point. And so, okay. The reason why I kind of assumed this was a second step is because I can already tell, right, we have NO times NO to get here. And so now let's do that, right? So we're saying, okay, so reaction 1 in our forward direction. Again, from the mechanism, it's bimolecular. So then, yes, it's going to be NO times NO, right, times our K1. And then, again, if this is fast, then it's equal to the reverse K1 times N2O2. So now, right, we can express our K2, obviously in terms of N2O2, so rewrite this. So we have it in terms of our reactants. So K1 times NO, and now we'll just do it squared, right? So we can start looking like the rate law over K negative 1, so just K. And so now I'm kind of getting at, right, now we're at our rate law. So we can plug this in, right, for N2O2. And what does that give us? What is this here? Yep, so right, so this matches the rate law. And so then we were correct. So matches rate law. Yay. Right, and then if you wanted to, you know, you could kind of think about how this third one would look, right? So I'm not trying to super confuse y'all, but just kind of like, what if you assumed, you know, the third step was the rate determining or slow? Yeah, exactly. And so that's where I could already kind of tell, well, if we had tried to express this last one in terms of this, so now we have to put N2O2, so now it's looking like H2 would be squared if this was a rate determining step. Do we kind of see where this is going? And then it's not going to match. Maybe I'll keep proving to you, right? So let's just see how this is wrong. Now let's do a wrong one, right? So let's say we made a wrong assumption. We're kind of confused. And, right, so wrong assumption. Well, let's just prove how it goes. So let's just say step 3 is limiting. So step 3 is slow. And so again, right, we could go through that same process. So, okay, we're just saying that our rate law has to be dependent upon N2O times H2. Okay, and then now we need to express N2O, right, in terms of this. And so again, so K2, right, into O2 now, times H2. And so now I'm just going through the math. Is equal to, so now the reverse rate, you can maybe tell that this is going to get not fun pretty fast. And so then, right, so then we have something like this of K2, N2O2, H2, or H2O is equal to N2O. But now we have H again, right? And so we don't have to necessarily continue all the way, but once you just start seeing that like things are not working out, so right now I have a H2, but I already have a H2 again, right? So now that would start implying that H2 has to be second order, right? So already not looking good. Right, so this is kind of devolving down, and all I'm trying to show you, right, is it doesn't match the rate laws. So once you don't have to go super crazy, right, but you just start recognizing, well, this looks squared already, and if this is determining, you know, it's going to be a lot more factors here, so it doesn't match. So basically, it doesn't match. Okay, so then just try again, right? And so again, right, you could have tested for the first step, but obviously the first step cannot be the rate determining, right, because that's just NO and NO. So there's no H2 involved in the first step, so obviously that can't be the rate determining step either. Does that make sense? Oh, so the first step, so you just kind of have to plug it in and try it, right? But right away we know the first step can't be the rate determining because it's only dependent on NO. So if our mechanism, if we had said that our rate law up here was only NO squared, then this would probably be the slow step, right? But because it's dependent on H2, then we have to keep looking. So that's why I went to step 2 there. And then I stopped there since, okay, I got my NO squared, I got my H2, I'm done. I know if I continue on to step 3, now it looks like it's H2 squared, and now things are devolving and not matching again. So that's kind of how I quickly run through it, but then again, right, you can obviously go through the more detailed math of it, and it should work out. Yeah, so the correct steps, again, we're starting here. So assumed that our second step was rate determining, then just rearranged, right, solve for our rate of N2O2 in terms of reactants, and then just plugged this in, right, for N2O2 to match our rate law there.
Oh, and you plugged it into the second equation.
Yeah, so then we plugged it into this one up here, right? Because we know that this is our rate determining step. The problem with this is this was an intermediate, right? And so that's where we got our NO squared out. All right, that's probably a good place to stop since now we really went in depth on that. But again, this is a good problem and a good example to kind of study what it all means because it's all put together here. Yeah. Yeah, well, it should, the notes should have updated. So yeah, it should update and be there. And then, so I'm going to go ahead and hand out your quiz, but yes, please take a break. Since I know we've been going hard at this rate law stuff. Hopefully that was 6, I kind of lost count. 4. So yeah, go ahead, take your break, and then you can work on your chapter 17 quiz, open notes, I probably have your rate law cheat sheet out to help you guys. The cheat sheet? In my office somewhere. I could go. Yeah, take a break, take your quiz. And then of course, if you still have questions about this rate law stuff, definitely ask me. All right, and then thanks again online. So I'll see y'all in lab. I know a few of you have emailed me about the quiz, so I'll get that over to y'all shortly. Stop the stream now.